Hello everyone. In this video we will continue to examine topic 5.1 electric fields, and in particular we will examine different representations of the electric field for different charge distributions. So, at this point we have a formula for the electric field, and it is quite common for students to think of this as the formula for the electric field, but be careful of that. This is the electric field due to a single point charge, not due to any arrangement of charges. This formula only works for either a positive or a negative charge. The only difference being that the negative charge will have a negative in front of this, indicating that the arrows would be going towards the individual charge. So be very careful with that. We also began to discuss how the electric field was represented. And what is most confusing about the electric field in some ways is that the same electric field can be represented in different ways. And in fact, you'll see it represented in different ways. There's the vector at a point representation, the vector field representation, and electric field lines. Now, the field lines tend to be the most useful and the quickest to draw in practice, so we'll see those a lot. But I'm going to emphasize number 1 and number 2 for now because in some ways they capture more accurately what the electric field actually is. And to do that, we're going to look at this electric field produced by this point charge using a simulation that you're welcome to pull up yourself and play around with. And in fact, I would encourage it. This simulation is the simulation called Charges and Fields. It's a PhET simulation and HTML5. So there's both an application for your iPad or other tablet if you like, or you can just go to it in the browser. So we're going to take a +1 nanocoulomb charge and we are going to place it in the middle of our space. And then we're going to show the electric field, and we're going to do it in two different ways using two different modes of representation here. The first is the sensor. So imagine you had a sensor that's like having a small positive test charge, and you put it at different points, and you wanted to know what the field was, or what it looked like, or what its value was. You could use this small yellow dot, and what that is it shows you the field at any particular point, okay? Notice this field is calculated using that formula we just examined, negative kq divided by r squared r hat. Okay, notice I can move it around. The closer I get, the stronger the field is, as expected, and the further away, the smaller the field is. But there's a sense in which the field still seems a little bit invisible, even though I can take more than one sensor and put it at different points, okay, in order to see what's going on. Right? So the sensor is important if what you want to know is the field right here, right at this particular point. But if you want a better sense of what it's actually showing, you can use a vector field representation. What this representation will do is show the field by placing an arrow at every single point around the positive charge. Okay? Now, in my crude drawing of it, I use the length of the arrow to indicate the strength of the field. But in this representation, okay, in this simulation, the strength of the field is actually being indicated by the brightness of the arrow itself. Okay, so if that arrow is brighter, that field is stronger, and we could show that here. So instead of having longer arrows, which tend to sort of climb on top of each other, if you can imagine drawing an arrow the size of this red one at every point around here, things would get very cluttered very fast. So what this representation is showing the electric field by using the brightness of the arrow for the strength of the field and the direction of the field indicated by the direction of that arrow. Notice that this field remains with the same structure as I move the charge around, okay? Although obviously the exact location of those tiny little arrows will change how that field is represented, okay? So if I move this over here, okay, you can see that the field always points out and away from that single positive charge, and it gets weaker as it goes out. And in fact, it's a 1 over r squared law, just like gravitation. Now, what happens when I put a negative charge on here? Okay. Well, we get the same sort of structure, except now the electric field is pointed in. Okay, and we can see that even with the sensor, that electric field is pointed in at every point, and it actually has the same magnitude because it's the same formula, as the electric field of a single point charge. Okay? Now, the best part about this kind of structure is that it allows us, or this kind of simulation, is it allows us to see what the field would be if you have lots of different charges. And we haven't talked about how that's going to work, although we will in a moment. But imagine I took a whole bunch of different charges here, and I'm just going to put them sort of at random points. Let's say you had sort of an ugly arrangement of charges, something that looked like this. Okay. Now, the vector field shows sort of a complicated field structure around here. But the real important point is to recognize that that definition of the electric field, that is, the force per unit charge felt at any particular point, is still captured. So if I put a small positive charge right at this point, right, it's not obvious what would happen sort of before you do that, but if you put this little dot here, you can see the force per unit charge would be well, I just moved it, but around 7.5 newtons per coulomb. Notice another unit is given, that's volts per meter. Those are equivalent. We'll talk about that in a bit. Now notice I can take this dot, I can take my sensor and ask about the field at any point inside this region, and it behaves a little chaotically. Like this would be really hard to analyze. But the virtue of this idea of electric field is that if we calculate the electric field at any point, we can then get the force that a charge placed at this point would be. This makes solving multi-charge problems much, much easier, as you might imagine. And we're going to look at sort of the field structure due to a few different charge arrangements in a bit, but I would encourage you for now just to play around with this simulation and get a sense of that field structure yourself. There are only a few you will need to be able to draw offhand, and we will come to those in due time.